right, so you're able to see the screen? Just want to make sure. Okay. Okay. So total filtration, like I said, is the inherent and the added. So it's the inherent and the added. So for inherent filtration, the tube window, the tube port, the oil, and the collimator mirror need to absorb low energy photons, or they need to absorb the same number of low energy photons that 1.5 millimeters of aluminum would filter out. So remember I said the standard material to compare filtration to is aluminum. So in other words, the tube window, the tube is made of glass, the oil is oil. The tube port window, it tends to be glass as well. And then the mirror is a type of like glass coating. So if you notice, with inherent filtration, nothing is made of aluminum, but those four items, those four things need to filter out the beam the same as 1.5 millimeters of aluminum would filter out. So that's what its unit of measurement is. So what this means is the glass window has to be a certain thickness, the tube port window has to be a certain thickness, the amount of oil that's in the tube and the thickness of the collimator mirror have to be such so that those components filter out the same number of photons as would 1.5 millimeters of aluminum. Does that make sense? So whatever those thicknesses are, and that will vary from manufacturer to manufacturer. You could have one manufacturer where the glass window was a little thicker, but maybe they had a little less oil in the tube. But the bottom line is those four components together have to filter out what 1.5 millimeters worth of aluminum would filter out. Does that make sense? So it allows some freedom there with the manufacturers as far as how thick do they need to make the collimator mirror, how much oil needs to be in there, how thick does the glass window need to be in the tube, as well as the tube port. So there can be some variations in how they manufacture those thicknesses, but in the end, all of those tubes need to filter out the same number of low energy photons. It needs to be equivalent to what 1.5 millimeters of aluminum would filter out. Okay. And then, of course, we've got our added filtration here, and that is made of aluminum. And so the thickness for this needs to be 1 millimeters worth of aluminum. So the thickness of the added filtration is 1 millimeters worth of aluminum. So when you add inherent and added together, we get 2.5 millimeters of aluminum. So the minimum total filtration is 2.5 millimeters of aluminum. Some textbooks, though, really to be technically correct, it'd be 2.5 millimeters of aluminum equivalency, because the oil and the tube window, the port window and the mirror, they're not made out of aluminum, but they're equivalent to what aluminum would filter out. So that's the reason why I mentioned this terminology here, aluminum equivalency, because you may see in some sources, instead of saying total filtration is 2.5 millimeters of aluminum, it may say 2.5 millimeters of aluminum EQ, which means aluminum equivalency. And, if you have a test question where that terminology is used, I wouldn't want that to end up throwing you. And it's just technically because the filtration is not all aluminum, that it could be reported as aluminum equivalency. Because technically, this could be 1.5 millimeters of aluminum equivalency, plus 1 millimeter of aluminum is 2.5 millimeters of aluminum equivalency. Okay. Does that make sense? Okay. So total filtration, 2.5 millimeters of aluminum. So when we look at recommendations, this is what the NCRP says. They say that 2.5 millimeters of aluminum is the minimum amount of total filtration that we should have on X-ray tubes that operate above 70 kVp. Can our X-ray tubes operate above 70 kVp? Mm-hmm. Yeah, absolutely. You saw that when you were in clinic. I'm sure you used over 70 kVp on some things, didn't you? Yeah. So for diagnostic tubes that we use, typically ours do operate above 70. So this is the minimum amount of total filtration, 2.5 millimeters of aluminum or 2.5 millimeters of aluminum equivalency. You do need to know these numbers as well, though. If you are in a facility and their maximum KVP is 70 and their minimum is 50, so if that tube only operates from 50 to 70 KVP, then the filtration only needs to be 1.5 millimeters worth of aluminum. That could be an office, maybe a podiatrist office where they're just doing feet, or it could be a facility where all they are imaging are extremities. And so they don't need an X-ray tube that operates above 70 kVp. Their tube can only operate between 50 and 70. So 1.5 millimeters of aluminum would be the recommended filtration. If it's a facility where the tube operates less than 50 kVp and it can't go any higher, it's less than 50, then the filtration is only 0.5 millimeters of aluminum. This really would pertain to dental imaging because they do use less than 50 kVp. For teeth, they're somewhere in the neighborhood of around 30 kVp, something in that neighborhood. Another area, though, that would pertain to medical imaging would be mammography, because in mammography, those KVPs are in the 30s, upper 20s to mid 30s for mammography. So dental and mammo. So you do need to know these numbers that are recommended by the NCRP. Okay. So you okay with that? So whoever the vendor is for an X-ray tube, they will follow these recommendations. Okay. Now, there are also regulations, though. Okay, there are regulations. When it comes to tube filtration, it can't be directly measured. And what I mean by that is when an X-ray tube gets installed, the filtration does have to be measured every year. So even in our lab, we'll have a medical physicist that will come and we'll check the amount of filtration that we have in our tubes. Well, you can't directly measure it. In other words, you can't take the protective housing off that tube and get a ruler out and measure what's the thickness of the glass window, what's the thickness of the tube port. They can't go in the collimator and measure the thickness of the collimator mirror. And they can't pour the oil out and measure how much oil is in there. You can't directly measure tube filtration. So what they do to measure filtration is they will measure beam penetrability. So they will measure the energy of the X-ray beam. So they'll make an exposure and they have a way of measuring the energy of the beam. And that will yield information about the amount of filtration that exists in that X-ray tube. So when they do this testing to measure the energy of the X-ray beam, it's something that's called half value layer, or HVL. So HVL is used to measure the beam quality or the beam energy, the penetrability. So what they do is they will place thin sheets of aluminum in the X-ray beam. So, underneath the collimator, they will they'll place thin sheets of aluminum. Like they may start out with 0.1 millimeters and make an X-ray exposure, and they'll measure that energy. And then, they could use 0.5 millimeters. They could use 1 millimeter. So they place these sheets in the beam, and they will measure the energy of that beam. And then they do these plots on semi-log graph paper. So they'll have semi-log graph paper that they will plot these dots on that represent the different energies. And then they connect the dots and they interpret what this curve looks like. And it ends up yielding information about whether or not there's the appropriate amount of filtration in that beam. And it is assessed annually. So this is a test that they do annually. And so what they're looking at with a half value layer is, half value layer means what thickness of material will reduce the beam to 1/2 of its original value. So basically this thickness of material here is considered to be, whatever this thickness is, this would be considered to be a half value layer. Because notice the beam has been reduced to 1/2 of its original intensity. In other words, we have 4 X-rays making it through this thin piece, but only 2 making it through this thick piece. So this thickness would be referred to as the half value layer. So they put this aluminum in the middle of the beam, and they look at what thickness of this aluminum will reduce the beam to 1/2 of its original value. We used to have to plot this when I was in the program. We had to purchase semi-log paper, and then you had to purchase this special ruler, which was called like a French curve. It was this kind of spiral looking type of ruler. And so this was something that we would have to do. This is not something that you all are expected to know nowadays. But when I came along through the program, this was something that our credentialing board would still test on, as far as knowing how the exact process worked. And they would even sometimes have a graph with that data on it, and we would have to interpret it. And that's back when we were able to do more quality control tests on the equipment. It's just now we're too busy to do quality control testing, and you have to have such specialized equipment now that it's something that really is not in our domain anymore, as far as actually doing the testing and having to interpret the results. But you need to understand that this type of testing does exist, and just some of the basics as to how this is done. So kind of what this looks like, and I had shown you all the half value layer curve back in the summer. So here's a half value layer curve, and what you're looking at is the original intensity of a beam. So for example, the medical physicist will come in and will make an X-ray exposure with no aluminum underneath the collimator. Okay, so they have no aluminum under the collimator. They just simply make an X-ray exposure. Okay, they make an X-ray exposure and they measure the intensity of that beam. And then they will start adding sheets of aluminum under that collimator, and they will look at, okay, at what point has the intensity been reduced to 1/2? And they'll look at the thickness of that material in millimeters, because they'll just keep adding sheets, whether it's 0.1, 0.5, or 1 millimeter, until it reduces that beam to 1/2 of its original value. So this is referred to as an attenuation curve, and notice that as the thickness of material increases, attenuation does this. Attenuation curves down, meaning that as layers of material are added, we have more and more absorption taking place, less transmission making it through. So this is an attenuation curve. And this is why we needed that semi-log graph paper and had to have a special ruler to plot this type of curve. And, what they ended up with, what you'd end up with ultimately is you would look at, okay, here my value has been reduced to 1/2, and what was that thickness of material? So this is something that the medical physicists do. I won't give you something like this on a test to interpret. This is something that we did have to do back, like I said, back when I came through the program, but medical physicists can still do something like this. However, most medical physicists aren't actually plotting this anymore because the X-ray equipment, the devices that are used to do quality control can actually calculate this internally. So you can make an exposure, and with a piece of equipment, it does the computations internally and it spits out a half value layer. So they really don't even have to go through this anymore themselves. But just wanted to show you, it was actually, it was a tedious process to go through. Because of having to plot all these data points and insert these metal sheets and then do the plotting. So all of that, basically to come to what's really important in understanding for the regulations. And this is posted in that link where I gave you the Code of Federal Regulations. There's a chart very similar to this in that Code of Regulations that I posted for you, and it lays out what the minimum half value layer requirements are. Okay, so if you notice, and this really is key because our X-ray equipment operates above 70 kVp. So the government says the minimum half value layer that an X-ray unit must have is 2.5 millimeters worth of aluminum. So what that means is if you operate the tube at 71 kVp, it takes 2.5 millimeters worth of aluminum to reduce that beam to 1/2 of its original value. Okay, that's the minimum amount of filtration that tube should have. At 80 kVp, the half value layer should actually be 2.9, which means at 80 kVp, it will take 2.9 millimeters worth of aluminum to reduce that beam to 1/2 of its original value. So notice as the kVp goes up, the amount of filtration to reduce the beam by 1/2 of its original value goes up. But this is considered to be the minimum amount of filtration. So when the medical physicist comes in and makes an exposure at 71 kVp, it should take 2.5 millimeters worth of aluminum to reduce that beam to 1/2 its original value. And if that's the case, then that X-ray unit passes inspection. And what that means is that X-ray tube is functioning properly. And we know that X-ray tube was manufactured with the proper amount of filtration. So to kind of tie this together, because it can get a little confusing, if the vendors follow this recommendation, so when the manufacturers, if they follow this recommendation and they manufacture the X-ray tube to have 2.5 millimeters of aluminum, that means that their inherent filtration is going to be 1.5 millimeters worth of aluminum filtration. Their added filtration is going to be 1 millimeter. So that yields 2.5 millimeters. So if the tube manufacturer follows these recommendations, when the government comes in or the medical physicist comes in and they do their testing, it should yield the proper amount of filtration. So again, the medical physicist cannot tear that tube apart and measure 2.5 millimeters of filtration. The way they determine that there is 2.5 millimeters of filtration is by inserting 2.5 millimeters worth of aluminum sheets in the middle of that primary beam, and that 2.5 millimeters should reduce the beam to 1/2 its original value. And if it does, then they know that tube was manufactured the right way. Does that make sense? Are you kind of able to follow that? And again, keep in mind, this is minimum, okay? X-ray tubes can be manufactured with more filtration than 2.5, but that has to be the minimum amount of filtration that that tube contains, okay? So the vendors will follow the NCRP recommendations for the thickness and amount of oil that will yield 2.5 millimeters worth of filtration. Then when testing is done, as long as you can insert 2.5 millimeters worth of filtration in between the collimator and the table, that 2.5 millimeters, if it absorbs half of the radiation output, you know there's adequate amount of tube filtration. I will show you tomorrow in lab what these sheets look like and kind of how they set them up so that you have an idea as to what this, what this configuration would look like. Okay. So what is the recommendation for the amount of filtration? What's the recommendation?
2.5.
2.5. Right. What's the regulation for filtration? 2.5. So it's nice that the recommendation and the regulation happen to be the same. Sometimes recommendations are different than what the government mandates, but you always have to follow what the government mandates. Okay. So you do need to know both the recommendation and regulation here. So you do need to know both of them, but fortunately they are the same. Okay, they are the same. Okay, and I'll show you the setup for this tomorrow. All right. So think about that, and if you've got questions about it, then we can also talk about it tomorrow. All right. So basically, that's tube filtration. Inherent plus added should equal 2.5 millimeters worth of filtration. That's the recommendation, and that's also the regulation. Now, we're still going to look at filtration, but now we're looking at filtration that is used for a different purpose, okay? All that stuff that we just talked about is a mandate, okay? It's a mandate that tubes have to be manufactured like that. Now what we're looking at are some things that are a little bit different. So we're looking at filtration that can be used to further reduce patient exposure, so beyond the mandates. And then we're going to look at something called compensating filters. So to start out with, some X-ray tubes are manufactured with an extra layer of filtration. Okay, this is something that is above and beyond the recommendations and the regulations. Do you recognize this X-ray tube from the lab? Okay. There's a dial, I don't know if you all noticed, but there's a dial up above the collimator knobs here. Excuse me. And we're going to do an experiment with this tomorrow, so we'll play around with this tomorrow. But when you look at the dial, it has numbers on it. Typically, we leave it in the 0 position because we don't want any extra filtration in the beam, typically, for the experiments that we end up doing in lab, okay? But we can turn this dial, and we can get different amounts of filtration added into the beam. For example, this is 0.1 millimeters of copper. So this dial is actually composed of copper. Okay? But again, remember, don't confuse this with the mandated tube filtration. This is something that is above and beyond that some vendors will add in. And it's up to the particular institution if they want to use this extra filtration or not. Okay? Like I said, we'll do an experiment with it tomorrow, but just to kind of give you an idea how this can further reduce exposure. This was an experiment that I had done with a knee phantom. I used 70 kVp, 3.6 mass, and I measured, the tube output was 267 microgray. And I didn't use this copper filter, so I didn't have this copper filter in place. Then I went up to 81 kVp, 1.8 mass. The exposure to the patient is 184 microgray. That's what came out of the tube, and no filtration in place. Okay, no filtration in place. Well, when you look at this combination of techniques, does it make sense why there is this change in entrance skin exposure? If you think about last semester, we measured tube output, and we changed technical factors and measured that. What did we say has the most impact on tube output? Which exposure factor, kVp or mass?
Mass.
Mass. So, even though I went up in kVp, I reduced the mass by half. That's why the entrance skin exposure is lower here. So remember, we talked about use the highest kVp, lowest mass, because that will yield the least amount of exposure, to the patient. So for a knee, I could use this technique, but I'd have this exposure, or I could use this technique and have this exposure to the patient. And 81 kVp was fine for the knee because I was using the grid, and so that's fine. 81 is not inappropriate for the knee. But then look what I did. I went back up to 3.6 mass. And why in the world would I do that? Because I've doubled the mass. So now you'd think that the exposure to the patient would go up. Well, yeah, it should go up to the patient. But notice what I did. What did I do to that dial filter?
Added 0.1 millimeters of copper.
I added 0.1 millimeters of copper. 0.1 millimeters of copper, okay? Since I added 0.1 millimeters, I did have to increase my mass to ensure that I would get enough photons to the image receptor so I wouldn't have a noisy image. But since that filter also absorbed a lot of low energy photons, look what happened to the entrance skin exposure. It went down. So even though I'm using 3.6 mass, I've got less exposure to the patient here than I did here. So some institutions might build this into the protocol. If their equipment has this copper filter, this additional filtration, they may build it into the protocol, but you don't decide to use this on your own. It has to be built into protocol for you to do that. But it is kind of neat. So here I was able to use that filter, and even though I went up in mass, there's less exposure to the patient here than when I used 81 at 1.8. Okay? And here's what the images look like. That's 70 at 3.6, 81 at 1.8, 81 at 3.6. Okay? Notice, even though the kVp went up, not a big difference in the contrast on these images. And again, remember, with digital, the processing parameters, those algorithms, have more of an impact on the contrast than the kVp does. So I was able to use a higher kVp plus use this extra filter and end up with less patient exposure and have an image that looks just as good as this image here. So that's, it's kind of neat. Did anybody see a dial filter being used when you did your rotations? Most places don't, but it is something that can be considered. It's something to be considered. And who knows, when you get out and you start working somewhere, it may be something that you suggest to the supervisors and say, hey, let me show you a way that we can reduce patient exposure. So you okay with that added filtration? Okay. And keep in mind, this is added filtration that this has nothing to do with tube requirements. This is just something above and beyond, okay? All right, and then the last segment that we'll focus on are filters that are placed in the primary beam to help balance out receptor exposure when we're imaging structures that have varying thicknesses or varying part composition. So these types of devices, most of them are placed between the collimator and the patient. So in other words, they're attached to the collimator. So they're between the collimator and the patient. There is one that is actually placed behind the patient. Okay, so we'll take a look at this and what this thing, raw radiation, what does this mean? But most of them are placed between the collimator and the patient. They may be made of aluminum. Some of them are actually composed of clear lead. It just depends upon the vendor. So aluminum or clear lead, PB stands for lead. So these devices are referred to as compensating filters because they're compensating for differences in the body structure. So we have wedge filters, trough filters, mediastinal filters, Furlick filters, and boomerang filters. Did any of you all see filters being used in your rotations? No one did?
I did.
Who did?
One. I did. He did it for C-spine.
Okay.
For something about it he used like KVP of 81, and then he went up on the mask, and he said he used a filter that he put it on the collimator, and basically, so like I guess it wouldn't be more exposure to like one part of the body. He like closed it.
Yes.
And it still had like the same image.
Yes, exactly. You probably used what was called a Furlick filter. We'll take a look at that. Maybe when you see it, you'll recognize it. But yeah, exactly. It helps to better balance out the exposure.
Yeah, because he said if he didn't use it, one part would be like totally black.
Yes, because when you think about the cervical spine, the cervical spine goes from up here to down by the shoulders, and we've got more thickness here. And, you have to use high enough mass to be able to image this part of the C-spine, but then that could be too dark for up here. So you could use a filter to balance that out. Exactly. So I'm glad you saw that. Did anybody see filters being used for feet or toes? Okay, so no one had.
Sorry. I did a calcaneus last week, and we were talking about using a wedge compensating filter, but for some, I don't know why we didn't. We just took 2 exposures instead, but they did talk about using it.
Okay, good. So you ended up having to take 2 exposures. All right, perfect. And I'll show you an example of that in lab tomorrow where it was done with film, but the same type of principle. As a matter of fact, we'll do an experiment using a wedge filter. So I'm glad you all talked about it. Did you see the wedge filter?
No.
Okay, good. I'm glad you all at least heard about it or had some experience with it. So this is what a wedge filter looks like. And this is one from our lab. It looks like a wedge. That's why it's called a wedge filter. So this is the tube side, and then our image receptor would be down here. Of course, our patient would be here. And that wedge filter, it slides into the collimator. That's why this wedge is mounted to this device that will fit into the collimator. And we'll use it tomorrow so you can see how it works. And if you notice, it filters. It filters out some of that beam. But this has nothing to do with filtering out low-energy X-rays to reduce patient exposure. This has to do with balancing out receptor exposure. So the way you would place this, say, for example, if you're doing a foot, you would place the wedge so that the thicker part of the foot, so towards your metatarsals, they would be here, and your toes would be towards this end of the wedge, because we don't need as many X-rays to image the toes as we do the metatarsals. Does that make sense? We'll do this setup tomorrow so that you can see it. We'll image the foot. we'll image our foot phantom that we have. So you can see how this wedge filter gets placed.
I'm sorry, you said the thicker part is placed near the what side?
It would be placed under the thinner side of the wedge because we need more x-rays to image the metatarsal area than we do versus the toes. Because the metatarsals, the structure of the foot gets thicker there. And so we need more x-rays for that part of the foot than we do the toes. So we would place the metatarsals under the thin edge of the wedge and the toes under the thick edge. So we'll do that setup tomorrow. A trough filter, this is supposed to, I try to get this to look like it's hard in 2D, but if someone were doing an upright chest x-ray, and so the x-ray tube is here, and this trough filter is mounted to the collimator. Okay, it's mounted to the collimator, and then you have your patient and then your image receptor. It's called a trough filter because it does look like a trough. It looks like a trough. And that trough filter was used a lot to do chest imaging when we had film in particular. You might not see it being used as much with digital, but we used it a lot for doing chest imaging. These are the lungs, and the reason we would use it is because we want a certain amount of photons to be absorbed so that the lungs wouldn't be too dark. But yet where this trough is, that coincides with the mediastinal area. So we want more x-rays to be able to get through because we need more x-rays to be able to get through the spine and through the mediastinum area. So that's a trough filter. Did anybody happen to see a trough filter being used? I didn't, guess as much. This is not as popular as what it used to be, but it helps to balance out the receptor exposure. So we get a more uniform looking image that gets displayed so that the lungs aren't too dark. This is also used for chest imaging. This is called a mediastinal filter. It also attaches to the collimator. And if you notice, this portion of the filter and this portion of the filter, that corresponds to the lungs. So that those areas of the filter here and here will absorb a certain amount of x-rays while it allows a certain amount here to go through because this is an opening. And you'll notice it's kind of angled to correspond to, how the mediastinum is, how the heart is positioned in the body. So here the filter will absorb x-rays so that the lungs don't appear dark, but yet it will allow x-rays to go through the mediastinal area. So it's the same thing, same purpose as a trough filter. It just allows for the lungs to receive fewer x-rays so that the lungs won't appear dark, but it's just a different type of filter. I do not have a trough filter, but I do have a mediastinal filter. In fact, this is one from our lab that I took a picture of. So I will show you this mediastinal filter tomorrow so that you can see what that looks like. And then this is called a Furlick filter. Does this look like what you used, Erin? This particular one? This is a Furlick filter.
Kind of, yeah, it looks similar.
Okay. So this is a Furlick filter, and you would place this part of the Furlick filter, and again, this is something that attaches to the collimator. This part of the filter would be towards the patient's head, and then this part of the filter would be towards the patient's feet. So if you're doing a C-spine, this part of the filter will absorb a fair number of x-rays for the upper C-spine. Whereas the bottom part of the filter here, you notice there's a hole, that will allow more x-rays through so that we can get that lower part of the C-spine by the shoulder area. This way it prevents the upper C-spine from coming out too dark. Does that make sense? You can also use this for cross-table lateral hips. So some of you may end up seeing that being done. So the C-spine and, lateral C-spine or swimmer C-spine and cross-table lateral hips, that's when this is used. And I'll show this to you because this is one that I imaged from our lab. So I'll let you see what this
with
looks
the
like.
hip, Miss
Pardon?
I did see this one with the cross table hip. I just didn't understand it.
Perfect. Okay. Does it kind of make sense now?
Yeah, I think so.
Okay. Yeah, and it so using it for the hip as well, it allows for better visualization of the joint space, so that the structure doesn't end up too dark and kind of getting a burned out appearance. So it does. It works really well. So all of those filters are placed directly on the collimator. This is an exception. This one is called a boomerang filter because it looks like a boomerang. We used to have one in the lab. We had loaned it, I think, to the library for, this was a number of years ago, and for some reason we didn't get it back. But anyway, this is a boomerang filter, and it is placed underneath the patient. So between the patient and the table. And it also helps prevent the shoulder from appearing too dark. I told you a few slides ago, I had the word raw radiation. Well, when you position, have you all done shoulders yet? Okay, so you haven't done shoulders. When you center for a shoulder, you're centered over here, but you're going to have a certain amount of light up above. You can only collimate so tight on a shoulder because you need to see all the way over to the end of the humerus. You need to see all the way over past the AC joint, and you need to be able to see, up above the clavicle. So because of where you center, we always end up with quite a bit of light on the top and on the side. And remember, wherever the collimator light is, that corresponds to where radiation is going to be. And so what happens is we get a lot of what we call raw radiation that doesn't hit the patient. It's raw radiation. It just goes right through the table and hits that image receptor. So it's a strong intensity. It's a high quantity of radiation, and that can make the image dark. And so this boomerang filter can be placed here to help absorb that primary beam, or what we call raw radiation. So it helps to lighten up that image to allow better visualization of the joint space. Anybody happen to see this being used? Some places will use it. Okay, so maybe you'll see it at some point while you're in the program, being used. Because I do know students have seen this in the past. But that's called a boomerang filter. Okay? So it'll just better even out the image receptor exposure by absorbing all of this raw radiation. Okay. You okay with that?
So what would you say the impact that compensated filters have on the patient exposure and image quality?
For the compensating filters, we'll see this tomorrow. We'll talk more about it tomorrow. But when you use a compensating filter, you may have to increase the technique. So you may have to increase the mass, which can result in an increase in exposure as far as compensating filters. Okay. The other type of added filtration, like when I showed you the copper, that can actually reduce patient exposure, because that type of added filtration will absorb low energy photons. Compensating filters that are used to balance out the receptor exposure can actually result in an increase in patient exposure. It can cause an increase, but that's okay because you're getting a better quality image, because the image is more uniform in brightness. So you don't have areas that are really dark and areas that are really light. Does that help you for patient? Pardon?
it's kind of flip flop. Like if you, in order to get a better image, like image quality, you would have to expose the patient more.
Right, exactly. And that's the trade-off when you use a compensating filter. You can get a better quality image, but the exposure may be a little bit higher to the patient. But that's okay if you're getting a diagnostic image. Yep, exactly. So it does help to improve the image quality. And then the last thing is looking at the impact of beam hardening on the emission spectrum. And let's see. What we have, 947. I'll tell you what. How about, let's go ahead and stop here because I want you to have you need a break before your next class. We can pick up with these 3 slides easy enough on Wednesday before we